All right. Today we're going to speak about blackbody radiation. This is radiation that the stars shine. The sun is approximately a black body. You're a black body, more or less. You radiate energy, and that approximately takes the black body form. All right, I guess I'm early, so I'll wait a few minutes. Isaac, do you want to make any announcements? You should, by the way, we had observing last night. Does anybody want to report on that? Was it good?
It happened Tuesday night.
Tuesday, I'm sorry, Tuesday.
So I'm not sure, actually.
Who went observing? Anybody here? What happened? You saw the moon, and what else? The lights were too high?
Yeah, and then the building that surrounds the field make us cannot be able to see.
Oh. All right, well, I apologize for that. We've been moved out of Campbell Hall, our old hall. They're supposedly some year going to demolish it. It's supposed to be, they should have demolished it by now, and it's been delayed 3 or 4 months. And we had a nice telescope up on top of that building. So that's been put in storage. We now have smaller telescopes that we can use for these classes. It's going to be that way for 3 years or more. All right. Yeah?
I have some questions. On the syllabus paper, it says that you can get extra credit for doing these lab reports.
The extra credit I had in mind would be if you go to more than one of these sessions, one session is expected of everybody. If you go to more than one, which they're not observing the same thing every time, you can write up your report about what you saw. These are not onerous reports. They just write up, just tell the GSIs that you went to the telescope and you saw what they did, and tell them what stars. We're, for example, going to look at the Cal stars. Beautiful set of binary stars that are blue and gold, just named for Cal. They're very fine. That's one example. Another example is to look at the moon and see a lot of the mountains on the moon. If the sun, we're not going to look at the sun, but we look at something called globular clusters, etc. Yeah. Oh yes. We're going to observe every week. And frankly, you can go to all week because there are GSIs from C10 manning the telescopes alternate nights. And they're all in the same place. So if Thursday or Tuesdays aren't convenient for you, pick another night. And everybody should go and enjoy it. Yeah?
Is there going to be a schedule for when the observing is going on?
I'm sorry.
Is there going to be a schedule for like the observations and their times and stuff?
I don't think we're going to have a schedule of the observations a given night, except you should just, any night you can go is fine, because the schedule will be based on what's up that night, and don't go one night and the next night, because the same thing will be up. But if you go 1 week, come back another month, and then it'll be a little different.
Where is it again?
Yeah.
I was just going to say that the GSI will send out a schedule on who is going to do the observations and when. We might send that out maybe every week or every 2 weeks. Because they'll be organized one that takes 4 nights every week for the whole semester.
4 nights every week. Yeah, okay. They haven't decided that? They don't know that now?
The Astro 10C is alternating days.
Yeah.
So they do like Monday, Wednesday, 1 week, and then Thursday.
You don't have to do it. You're not doing every Tuesday?
We're doing every Tuesday.
Okay. But basically, you can go any night, any weeknight of the year. And you all want to look in a telescope. You should do that, and regain a little bit of the heavens and see the beautiful sky. Now, this is the spectrum of the sun. We're looking at a very detailed spectrum here. Each of these, this is one spectral channel, and we've folded it up to each other because in detail, you spread the whole spectrum out. That's what you really look at. This is a picture of everything folded and put on one. And you see all these lines. What are all these lines? Okay, these lines were first observed in the sun a long time ago, and scientists had no idea at first, or they had a good idea what they were, because they saw similar elements that make similar lines on their spectra. One line in particular made something that they didn't know about. It was called helios. Helios means sun. Helium was an element they named. They had never seen that on the Earth, but helium got its name because it's close to Helios. All right, so I'll talk about that. We'll talk about that now. Okay. We talked last time about the fact that you can see primarily in the visible band. That's the window we can see. Our evolutionary system adopted to look only in that band. It didn't look in these other bands. But with modern technology, astronomers can look at all these bands, and we learn about the universe in different ways. Okay, so why the sunsets are blue and the sky blue and the sunsets are red has to do with what I called Rayleigh scattering. This is named for Lord Rayleigh, who first talked about it. And this is scattering of anything of light by small particles. If you shine blue light through a cloud, it will scatter more than if you shine red light through a cloud. And because of the color dependence of the Rayleigh scattering, we have a blue night sky. We have a blue sky. Okay. We have a blue sky rather than a red sky. So we have a blue sky because of Rayleigh scattering. And you'll see what goes later. All right. Here's a burner, old-fashioned burner. You're taking a picture with a camera that sees primarily in the infrared. All right. And here is the same camera taking a picture of a guy. Now, he's got two cups, one containing hot water, one containing cold water. This camera takes a picture in about 10 microns wavelength. All right, and it shows him very clearly. He's glowing at 10 microns. But so is this cup. And this cup is not glowing. Why not? It's cold. When it's cold, it glows much less than when it's hot. The hot water, or whatever is in there, hot coffee, glows much more than here. So astronomers, by looking at distant objects and the infrared emission of those objects, can tell right away that what the temperature, approximate temperature of the planet or star happens to be. And that's a very powerful tool. After all, we want to know the temperature of things. For example, we pointed this at Venus, and scientists knew that Venus was incredibly hot. It has a temperature of about 700 degrees Kelvin. That is hot enough to destroy all electronics. You know, your computer doesn't work at 700 degrees Kelvin. You don't work either. You know, you're dead if you get out on Venus. Why is Venus so hot? Why is it so hot? It's not that different from the Earth. It shouldn't. You don't think it should be so hot. And we'll talk about why it's so hot later in the course. But they could tell that by looking at an infrared radiation. Instantly they knew that. It had to be. Okay, now this black body radiation I've mentioned is a special radiation. It's known as a perfect emitter and absorber of radiation. Here's an example of a black body. This black body is just anything. It's a cylinder or a sphere painted black on the inside, and the thing works by the radiation more or less is emitted. Anything comes out, and the radiation comes out this hole. Now, what scientists discovered was, in trying to understand how this radiation worked, and this was an important subject for study in the beginning of the 20th century, before then, they first of all realized that the radiation only depends on the temperature of this body. As you make it hotter, it shines more. If it's colder, it doesn't shine as much. Now, they discovered that this black body radiation gave a broad emission. If it was a hot body, it had a spectrum like this. A cold body, colder, colder. All right? Now, first of all, everything was characterized on the Kelvin scale. You all know Kelvin? All right? That's something you have to know from chemistry. Remember that 0 degrees Kelvin is absolute zero. It's minus 273 centigrade or minus 460 Fahrenheit. Very cold. A change of 1 degree in Kelvin is a change of 1 degree centigrade. That means that Kelvin, 0 degree centigrade is 273. 100 degrees centigrade is 373 Kelvin. The transformation degree Kelvin is 1.8 degrees Fahrenheit. That's the same transformation as to centigrade. Okay, so the spectrum of these objects was characteristically different. Now, this is a linear spectrum. Linear here and linear here. If I plot those, if I take the logarithm of this axis and this axis, okay. The radiation emitted in terms of the total radiation emitted per unit area per second was proportional to T to the fourth. This radiation was equal to some constant, we call it sigma, times the temperature to the fourth power. That is expressed here. These temperatures are going up as the fourth power of the temperature. And the peak of the radiation, the maximum wavelength of the radiation, scales inversely as the temperature of the object. Here is peak, 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 and this scales inversely as the temperature. All right. Now, if you plot it in a logarithmic scale, 0, 10 to the 2, 10 to the 4, 10 to the 6, you can see how the curve looks absolutely the same in the different wave bands. 15,000 degrees, 5,800 degrees, 3,000 degrees. These are characteristic temperatures of a star. The sun is 5,800 degrees. And note that through the band, the blue star is called blue because the blue light wins over the red light. A blue star, like this thing, 15,000 degrees, emits red light. but it's overwhelmed by the blue light. So you look at it and you say, oh, that's blue. This guy, the 3,000 degree star, you look at it and you say, oh, that's red. You don't see the blue light that's emitting. I mean, that's just the way it is. And we see the sun as a yellow object. A yellow object is primarily peaked in the middle. All right, so that is, that's just how we perceive color. If we had fancier eyes, we would take a whole spectrum of the color. And you'd see, oh, it's got this much blue, that much red. Unfortunately, we don't have eyes like that, but instruments do. So you depend on scientific instruments to disperse the light. Now, we also know that, that if you hold a poker over a stove or over a fire, it starts off black, it gets redder, redder, redder until eventually it looks white to you as it gets molten. All right, and that's the same as this 3,000. This is a bit exaggerated. This is probably a temperature of 500 degrees and up to 1,000 degrees or something. This is exaggerated. All right, but the colors get bluer and bluer as it gets hotter. Now, that is backwards from what you think of temperatures. You usually think of temperatures as red being the super hot and blue being super cold. Unfortunately, that notation has pervaded the common literature, but that's completely wrong. It's backward. And when they talk about what color light are they selling at a store, they ask you that question. You're going to buy LED lights, and they say, well, you want a blue light or a red light, or do you want a warm light or a cold light? And what is associated? They associate a warm light as being red and a cold light as being blue. Well, according to, that's incorrect. That's backward. But okay, you have to learn that the optical industry has it completely backward, and I bought a bulb the wrong type because I followed the scientific notation of how hot and cold goes, but I was confused by that. All right, now down here, 310 degrees. That's the temperature of a human. 98.6 or whatever is right down here, and it follows a black body curve as well. But we don't really emit anything that you can see in the visible. We're very visible. The visible light we see of us, I see you, is not because of your internal glow. It's because there's reflected light that defines your colors. So don't be careful. If I had infrared eyes and turned off the lights, I would see you as glowing objects. But we don't have that power. It's more than one wave. It's more than a whole scale. It goes from 10 to the fourth to 10 to the less than 10 to the 3 in order to transfer from infrared, which is infrared is over here, transferred into the visible. All right. So yet we do emit this warmth. Now, the warmth shows up as the fact your body radiates heat whether you're doing any work or not. And that's why you have to eat food, because all the energy has been dissipated into space. Everybody does that. If you're dead, you don't radiate anymore. Your temperature goes down to the temperature of the room, or wherever you happen to be. But this is why if you pack a lot of people into a room, it gets warm. It's because of their black body radiation. If you want it to be cold, you have to turn off their black body. And that means kill them. And then they'll be cold. Okay? All right. All right. So why do humans and other animals detect only visible radiation when it's a small part of the electromagnetic spectrum. Anybody? Why do we detect only a small part of the electromagnetic spectrum? Anybody? Yeah. Evolution, that's true. Evolution makes that happen, clearly, but why does it favor that?
If we have too much information, we get confused.
Okay, what?
If we we're detecting too much, it'd be hard to decipher all the information you get.
Man, that'd be really neat if you're a computer, if you're a bionic device with all these. No, that would be hard.
The frequency's too high.
That's true, but there's another reason. Let me say, where does the sun give off most of its radiation? To give you a hint. UV. Yeah, not really. It doesn't give off. Most of it's in the visible band. All right. The wavelength of green light. If you got that. The real advantage, the wavelength of green light, the peak wavelength of 5800 degree light, just sticking it into the formula, turns out to be green at 5,000 degrees, and that's the peak of the emission. And obviously, it's evolution that puts our ability to detect light where the sun puts the most light. Doesn't make any sense to have it anywhere else. All right. All right, here's a question for you. I said the red star doesn't shine as much as the blue star. Let me go back here. Here is red light. Oh, shoot. Here's red light, and here is blue light. These are drawn properly to scale, or more or less, and an object that is blue emits tremendously more radiation than an object that is red. It goes as the fourth power of the temperature. All right? So now here's the question. Okay. Two stars are shining. The red star is quite luminous. The blue star is faint. You see them in the sky. The red star is a bright star. You can see it's bright. And the blue star you see as a faint star. All right? So, which is closer? You can just look at them and say, I'm asking you, let's assume the two stars have the same size. All right? Which is closer and why? So talk about this to your neighbor and get back to me. Which of those stars is closer? You know? You know? Okay. All right. Let's have a vote. Maybe you should vote by putting your finger close to your chest so you don't embarrass yourself if this is the wrong answer. All right. I will give you... Oh, Isaac, did anybody make those red, green, and blue? All right. I'm sorry. We should have those up by now. Okay. A will be 1. Nobody's got their hand up. B is 2. C is 3. Okay? Hand down, not so high. Hand down. You don't want to tell your neighbor. You don't want to give it away. 3 is, all right, let's see it again. Okay. 4. 5. Okay. So most of you got it. The red star, which is fainter than the blue, that is intrinsically fainter. It's not putting out as much radiation. It's like a 20-watt bulb, and you're comparing it to a 100-watt bulb. Obviously, the 20-watt bulb is only going to be brighter to your perception if it's right in front of you compared to the 100-watt bulb. And that's astronomers use that trick all the time. We have to use that trick to guess, not guess, but to estimate the distance of stars. So that's well known, and that is the first thing, the first quantitative thing we're doing with the distant universe. So we're making use of the fact that the stars shine, and they shine according to that. Okay. Now the this is called thermal radiation when I can characterize it with a temperature. There's a lot of different stars. They peak at X-ray, gamma rays, X-rays, ultraviolet, visible, infrared. Visible light is mostly emitted by stars. Ultraviolet light is emitted by very hot stars, and we'll see it emitted by supernova remnants as well. X-rays. Amazingly, if you look at a cluster of galaxies, a whole bunch of galaxies grouped together, you see X-ray emission, just like the emission of an X-ray that the doctors shine through your body. What is that coming from? Well, you can say that on thermal radiation, the temperature of that cluster is of order 10 to the 6th, 10 to the 7th, or 10 to the 8th degrees. And that is a measure of its temperature. What does that mean? Well, astronomers have measured this, and they see it, and there are a lot of papers written about what it means. Now, I can tell you what it means, but that's later. Infrared radiation is given off by cold stars. If you're going to look at the planet, like Earth, from a distance, it emits primarily in the infrared. Okay, so that's one way. Radio is not astronomical objects. Generally, it is the emission of cold gases, and we'll see that later as well. Okay. Okay, here's a question. Clusters of galaxies are seen to emit X-rays. What temperature does this tell us the gas in the cluster must be? 10 to the 8th, 10 to the 5th, or 10 to the 2 degrees. All right. Who says 10 to the 8th? All right. Who says 10 to the 5th? 10 to the 2? All right, the answer is 10 to the 8th. This is the domain of X-rays. Ultraviolet is the domain of material that's 10 to the 5th degrees. If it's cold, it's only, yeah.
Could you go back to the previous slide? Oh, okay. Thank you.
Okay?
Yeah.
All right. So this material is in the text. You don't have to memorize anything, but you've got your notes and read them. I'm never going to ask you details. You know, this course, I don't know what you learned before, but memory of all this crap is silly. It's completely silly. I mean, the course is teaching you methods. There are a lot of facts on the way. Don't worry about the facts. Just understand my methods, the scientific method. And we do gather a lot of facts, but the method is important. All right? Okay. All right, now, it turns out that this can all be grouped into 3 laws of radiation, known as Kirchoffs' 3 laws. First, radiation is a body. heated to incandescence emitted continuous spectrum. Black body radiation is such an object. All right? A filament in a light bulb is an object like that. You are an object like that. A gas heated to incandescence emits a bright spectrum of lines, and we'll see that in a minute. But a cold gas placed in front of a hot solid produces bright continuum. The solid produces this huge continuum, the continuum, and superposed with dark lines on it. That is more or less what we see in the sun. We see the hot sun illuminated cold gas in front of it, and that's why the sun has an enormous number of these lines. Okay. Now, here are Kirchhoff's laws. Here they are in action. Here's a hot light source, a bulb. And the light goes off this way. It's dispersed by a prism. A prism will disperse the light the way we know prisms do. And you look at the spectrum, and it's a continuous spectrum. If the hot light source goes through a thin cloud of gas and scatters, it'll scatter primarily in the lines of whatever makes up this gas. If it's made of hydrogen, you'll see hydrogen lines over here. And you spread the light, and what you see is a spectrum of these lines. But if you now shine a light through it, you've got a hot light source, a colder cloud of gas, and the light continues, and you take a spectrum of it, you see an absorption line spectrum. Now, why do we see these three different spectra on just a simple light bulb? Well, here's one thing you can say. All right. Okay. Now, here on the upper left, this is a neat, Isaac, this is a neat, I'll show you this. This is really neat. All right, a star emits all these lines. It emits all this light, blue light, red light, everything in between. It passes through a cloud of gas. All right. Here, first of all, I'm sorry. I'm going to start this way. Okay. Now, the thing, the cloud, the star emits light, and the telescope is right here, and you measure it in the telescope, and you see a continuous spectrum like this. So you see the spectrum, and it's continuous. There's no lines in it. Now, let's put a gas cloud in this system as well. The light shines through a gas cloud, and then it hits the telescope. All right, so first of all, it has hit this cloud. Now the cloud is colder than that shine, than this bright light, and as it goes through the cloud, every once in a while, a photon is kicked out. It's scattered. So the photons are scattered by the clouds. That means there's less light to make up what we had before. If they're scattered, they will be scattered primarily at the spectral lines of that element. The photon comes in exactly at the right wavelength to excite hydrogen or something else, and that scatters the hydrogen lines. So what it leaves is a spectrum with lines in it. Here, the lines were here, and the spectrum shows dark bands. Exactly that is seen for the sun. Now, if you take another telescope, Okay, now I move the telescope off to the side. Here's the telescope. And the only light it sees is the scattered light. Most of the light from the star goes through the cloud and just keeps going. But occasionally the light gets scattered out. What light's going to get scattered out is that light which corresponds to emission lines or corresponds to transitions in the material we're looking at. Now, you've all taken chemistry, and right? No? Not here, but in high school. Okay. Shaking your head. Who's taking chemistry? All right. So everybody, you got to take chemistry to get into Cal. And you know that every element has transitions at different wavelengths. Now, astronomers make use of this, and we study the spectrum of the gases and everything. Remember, all we can do is point our telescope up. We don't go to these gas clouds to see anything. We have to see what they tell us. All right, so we happen to look at the side of a particular cloud, and we see emission lines. Those lines are because of the elements in the cloud. Now, they scattered the light. The light was scattered out of here. And this is the photons that used to be in the light. All right, I'll take it back. By conservation of photons, the light was going here, but now it's been scattered off. It was here, but it's now no longer there. This is Kirchhoff's law. That's all there is to it. Okay? Any questions on that? All right, so this was noticed in the 1800s. People knew about this. Okay, so a question then. We had on the first slide of today, we saw emission from a continuum emission of the sun, and we saw lots of absorption lines. How does the sun produce these absorption lines? Is it hot gas in front of a cold emission, colder gas in front of a hot background, or cold gas mixed in with warm gas at the same position? All right, who says A? Put your hand up if you say it. B? All right. Who doesn't vote? Who's not voting? Some of you didn't vote. All right, C. Nobody votes C. Well, one person votes C. All right? I'm sorry. This is because some of the gas in front, the B is the right answer. Some gas in front of the hot star is actually a little colder, and that gives rise to the absorption lines. All right. Those lines they represent gas. That the gas comes in front of them, and they scatter the light all over the place. All right. They don't keep the light going straight to us. All right. All right, now, there's another thing we can do with these lines. And this is called the Doppler effect. Who knows what the Doppler effect is or studied it? All right, a few of you who've taken physics know what the Doppler effect is. This is incredibly important for use to study this universe. And this is what tells us so much about the universe. All right, so we, for example, a cop shines a Doppler radar at you, and then you end up with a ticket because you went 58 miles an hour in a 50-mile-an-hour, 20-mile zone or 25-mile zone. How does he know it was 58 miles per hour? It's not because he's a good guesser. He looks at the device, and it tells him 58, give him a ticket. All right? So that's one. How does that work? Now, the people who worked on this go way back, 1780 to the 1800s. Bunsen, you all know what a Bunsen burner is. Fraunhofer, he's the person who was named the lines, the absorption lines in the sun are called Fraunhofer lines, after honor of him. And Kirchhoff, who invented this spectroscopy. Okay, now, Doppler effect, let me go skip a little bit. Okay, first of all, why not, just a minute. I have these things mixed up, sorry. Okay, here's the Doppler effect. Now, how many of you have seen this? If you're standing next to a train, the train's coming at you. If the train is still, is stationary, he puts out wavelengths of him getting ready to go, and the wavelengths travel, and everything's fine. But if he's moving to you, he travels, and the sound waves seem to get higher pitched. But if he's traveling away from you, it gets lower pitched. Have you ever noticed that? A train goes by, zoom. Okay? No, that's not a very good train whistle. Who can make a better train signal? Anybody? Somebody want to try that? Isaac, are you making better trains? Go ahead.
No. I mean, not a train signal, not a train signal, but the ambulance. When an ambulance passes by, it goes like.
Oh, but that's a signal he goes by. He's modulating a signal. But somebody give me a sound of a train or something. Choo-choo. Well, that's so good. Okay, fine. All right, but you all know what I mean. There you go. That's perfect. Okay. Now, here's what happens with light. If a light bulb is moving fast to the right, the wavelength gets compressed, but it moves slow. It appears to be stretched out to the other direction. He looks red or blue, depending which direction he's going. And you can see this as more or less each wavelength gets compressed. This will appear blue because there are more waves of higher frequency of the light. This is red because it's stretched out. So this Doppler effect is visible on all the objects. Okay. Now, we use this all the time. For example, if you look at a star and you see certain emission lines in it, the star will have a lot of absorption lines, just like the sun. And the spectral features will be, this is 4,000 nanometers, 400 nanometers, 700 nanometers from blue to red. If you look at this star in a galaxy, often you see that they're shifted a little bit to the red, shifted this way. They're red shifted, therefore. Redshift means the lines are shifted to the red. We observe redshift all the time. All the galaxies appear to be redshifted, and his galaxy is smaller because it looks further away, and his redshift is exactly further. And here is a galaxy that looks just like a point on the sky. It's so far away. His redshift is further. Now, I'll tell you what that means later, but right now, just think of it as the Doppler effect that is visible on these objects. All right, direct use of the Doppler effect. All right, so this is a powerful tool if we disperse the light and record the dispersed light. It's a very powerful tool for estimating what's going on. This is why so much telescope time is used to study it, and I'll tell you why a little more. Now, the Doppler effect, first of all, c, the speed of light, is the same. Okay? It is the same to all observers. We'll talk about why that is a little later. Okay, wavelength of light does depend on the motion of the observer. If the wave's coming to you, it appears to be, the waves get shorter. If it's going away, they get redder. Okay, now the same effect occurs with sound waves as well as light waves. Okay, it's convenient. Okay, the equation governing the Doppler effect is that the wavelength observed over the wavelength emitted is 1 plus V over C. Okay, now, the man with the Doppler radar shining at you, he shines a gun at you, say it's exactly 900 megahertz, sends out a beam, very nicely tuned to a narrow line. If he gets a line back at him at, say, 902 megahertz, okay, that means you are going away from him. It's a bigger wavelength. Let's say it goes 809. Let's say 900. It goes to 899. It shifts by 1. Now that's not much, but a radio detector is capable of seeing that shift. And if he shifts by 1, that means that wavelength is V over C plus the equation is this is equal to 99%. That means that V over C must be 1%, and that means that you are traveling at 1% the speed of light. That is pretty fast, because normally you travel at, say, 60 miles an hour is, what percent of the speed of light is that? What's the percent of light? Anybody calculate it? Tell me what that is? It's a lot less than 1%. Okay, it's 10 to the minus 6, I think. The speed. V over C will be 10 to the minus 6. All right, so you've got to be able to detect this very sensitively, and that can be done. Okay. All right. The crests of waves pile up in the forward direction, stretch out in the backward direction. Blue shifts when they pile up, red shifts when they stretch out. Okay. Now, that's new, and the equation is the same. This is the same equation. The shift in wavelength is divided by, is equal to nu over, oh gee, this is V over C. I'm sorry, that should not be a nu. V over C times the rest wavelength. That's the same equation. All right, so you have to be, if you're really going to make a change that's substantial, you have to be moving at a good speed, close some fraction of the speed of light. All right. How does that happen? Well, we'll talk about it in the course. All right, now, this is an incredibly useful tool in astrophysics, and I'll show you why. Examples, hold on. For example, if one looks at a planet orbiting a star, what actually happens is the planet is offset from the center of mass. You can think of it as a teeter-tot with your younger brother, who weighs only, he's a little guy. He weighs only 30 pounds, and you weigh, say, 150 pounds. So in order to balance on the teeter-tot, you have to sit near the middle, and he sits on the long axis. He's out there ways. And then you can balance. Well, that's exactly the same principle as the star. This guy, he weighs a lot more than the star, and in order to keep him balanced, he's got to be on the other side of the teeter-tot. All right, so star's heavy. All right, but you can see this star is invisible to see he's invisible. He shines only in infrared. But this guy emits in the blue, or throughout the spectrum. And you can see, if you're off to the side, you're way out here, you may not see that object, you may not see spatially anything. It looks like a star, a point, it doesn't move. But you can see the spectrum is changing. Back and forth, just like the star. Back and forth, back and forth. Why is it changing? There's no other explanation other than a planet is orbiting the star. So we determine that a planet, and you can use Kepler's laws to determine the mass of the planet. Very powerful technique. So because of this, you can guess the mass. If you see the star's color, you know pretty much how much it will weigh. I'll show you how that's very precise. And so you know it's a 5 solar mass star orbited by something lighter, and you determine that it's part in 10 to the 3 or something. Now, if you look at a galaxy, galaxies orbit, the stars orbiting a galaxy are in a complex pattern. There's more or less, think of this as a solar system. They orbit faster in the center than they do on the outside, but it doesn't have it's not really a one mass that is governing it. It's all the mass of everything. You can see this from a distance, cosmological. You measure the spectrum of the galaxy, and you can see that it is shining. And that is a very, very powerful technique to measure galaxies. And we'll talk about why that's powerful later. Binary star systems, like the Cal star, they're heavy. You can possibly see, many times you can see the emission the lines from one star and the other star, and you'll see them crossing back and forth, back and forth, back and forth. Then it's quite clear it is two stars orbiting each other, binary, so that you can tell right away. Or, if you can see a galaxy cluster, you may see these galaxies. Now, then nothing moves. This has such a long time scale to change its orbits. A time scale to change the pattern is 1 billion years. You're not going to wait 1 billion years, obviously. But right away, you know you can measure the different velocities of all the objects. And the velocities are different, and they're different because of random motions, so-called virial motions that are in the galaxies. And this is a powerful technique for measuring the mass of those galaxies. All right. Okay, for example, you can, if you look at an emission line, you can do things very fancy. For example, the intensity of a line might be fairly narrow, and you might see the line, the spectral line, might be wider. Why is it wider? Well, you would say the star is rotating. If it's rotating, it might be blue shifted, or here it might be blue shifted a lot, and here it'll be red shifted a lot. The blue light ends up here, the red light, well, I can't even tell the difference, ends up on the other side. All right, so you can tell by the line shape how fast it is rotating. It is an amazing tool how you can use it to study all these properties of distant universe. We don't have to go there. We can learn about it by studying carefully all the things we know and applying the physics we learned in Astro 10. Okay? And a little more. All right. Now, the 19th century, scientists knew that the emission lines were characteristic of each atom. You learned all this in chemistry, and you also learned what the explanation was. The explanation made no sense at all. The explanation of quantum mechanics to explain this is completely ridiculous. Everybody agrees it's insane. All right. The unique atomic signature was nutty. But we now say the atomic signature is because there's a level, a ground state level, so-called level 1, and all these other levels, 2, 3, 4, 5, and getting up to the continuum level, and each of them has its own wavelength, and blah, 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 blah. You learned all that, right? Okay. Question? All right, so chemistry. Now, you know, that was a domain of physics, because at the beginning of the 20th century, nobody understood this. The physicists were trying to understand this, and it led to the invention of quantum mechanics, a very physical theory. A lot of Nobel Prizes because of that, and a lot of people who accepted, didn't accept it. Einstein never believed quantum mechanics because some of the laws, but he understood this. All right, so these lines are characteristic, and they're fortunate for astronomers who use them. All right, now for example, this is a galaxy with a catalog number, 2775, some number of a catalog of many thousand galaxies. A spectrum of it shows this amazing absorption lines. This is angstroms. That's 4,000 angstroms is 400 nanometers. So this is blue. This is red. It shows a few lines that are strong. And those are characteristic lines. This right here is a line of calcium seen in the galaxy. Now, this is the spectrum I took 20, 30 years ago. That's an absorption, so-called absorption spectra line. This is absorption spectra of the galaxy, the whole galaxy at once. If you point your spectrograph instead at the Orion Nebula, you will see this. And you see lines of helium, oxygen, helium, neon. All these elements are showing up on the emission spectra. And this is an emission spectra. You're seeing to the side of a region that was illuminated by a bright light and shines this to you. Okay? This is characteristic of Kirchhoff's laws. And that's the object. Okay, you also learned about how the electrons jump between levels from 1, 2, and 3, or you can say it's up here and they jump down and down from level to level. This was it didn't make a lot of sense, but nobody wanted to explain it, but that is it. And it's explained on the equations. And you don't want to, believe me, you don't want to see the equations, but the equations give it very clearly why the spectrum is what it is and all this other stuff. The equations are very simple, according to us, known as the Schrodinger equation, and it's amazing that it works. Because of the math, physicists understand what's going on. All right. So the spectroscopy is incredible diagnostic. We make use each element. And molecules are different in their parent atoms, as you know. The width of the spectral feature is a result of the Doppler shift. Gas is hotter, will be seen in emission. All right. Gas is colder than the background. We'll have an absorption line. That was noticed a long time ago. And Fraunhofer lines is from cold gas near the surface of the star is absorbing the hot gas underneath it. Now, this cold gas need not be really cold. It only means that it's cold relative to the background object. For example, the background object might be 6,000 degrees Fahrenheit, 6,000 degrees Kelvin. The foreground object may be 4,000 or 5,000 degrees Kelvin. By the definition of cold and hot, that is still all you need to produce a absorption line. Just having a temperature gradient that you can see through makes the absorption lines. So when I say cold, I just mean relative to the other stuff. It's not really cold. Okay, so what I try to say is that this measurement of spectra is an incredibly useful tool. It is the most powerful tool that astronomers have. Okay, so fortunately you all took this before when you took chemistry, and you know what's going on. Okay, let me show you another movie. This one's okay. Okay, so this one is showing the levels of atomic levels in an atom. Now you know that this is really a fake way of doing it. You're not supposed to draw these levels at a fixed location because the electron, it sort of gives you the picture of the electron jumps. But that's not really right. The electron exists in a cloud around the star, around the nucleus, and the cloud shape changes, but it is not jumping. No time does he really jump. But that's okay. For us, we don't care. We'll use the wrong notation. All right. So here I'm going to... Okay, now what happens is an atom comes in. All right, he comes in. Let's try again. Bang. All right, he comes in, and it excites. This one comes in, didn't do anything. Okay, it excites the atom is excited up to an excited state. It doesn't stay at the excited state for too long. Okay, now as it decays, let's see where it goes. Bang. Now he puts a photon off in some random direction. So the atom doesn't know how it got there. It just emits the photon anywhere. And this is an example of how the photon scatters the light. It scatters the light. That is primarily light which can cause it to jump from one level to another. The photon has to be exactly the right energy, and then it's absorbed and jumps. Okay? Now we can look here at the levels, and you'll see where it is. Let's try this again. It jumped up to there, it jumps down. You note that it doesn't always jump up and down exactly. Let's see. Up there, you see it jumps down to level 2 and then down to level 1. This is a mechanism whereby you get the lines come out in different wavelengths than they went in at. This is characteristic of nuclei, of atoms. Okay. Note also that the photon comes out, it came in with an ultraviolet photon and it emitted a visible light photon. So that is important. For example, the lines, these basic lines of hydrogen here have 10 electron volts between them, a little more than 10 electron volts to get from the ground state to level 2. And so the ground state is 10 electron volts. What is the energy of a, what energy is that? What wavelength is that? Anybody? Remember that the energy goes as h nu. It's proportional to the wavelength, to the frequency. What is the energy of a blue photon? Anybody remember this from chemistry? Huh? Nah, it's a random fact. All right, it is about 3 or 4. What is it? It's 5 electron volts. You remember what it is? Give me a number. 7, 6. I think 5 is a good number. See, here's a graduate student who studied lots of physics. He took tons of physics before coming to Cal. I studied it so long ago. I'm excused. And the stroke killed it. But he doesn't remember it either. So don't remember it. It's not important to remember. But I'll just tell you that a photon coming out in the blue light is 5 electron volts, 3 electron volts, let's say. And a photon coming out in the red light is more like 1.5 electron volts, or 2 electron volts. Okay, and so the photons coming in at 10 electron volts, which are needed to excite at least got to be 10 electron volts, up to 13 electron volts. These are infrared. These are ultraviolet photons. The star is emitting ultraviolet light. It's absorbed by the gas cloud, and the gas cloud then emits visible light. And this is a mechanism for transferring the spectrum from ultraviolet into visible. Okay. All right, now, in Max Planck was an important name as a scientist who lived during the 19th and 20th century, and he did not understand something. He's trying to understand why the black body radiation has the spectrum it had, and he needed to introduce a quantum principle. Nobody really understood what quantum mechanics was. Nobody, these guys went to school and there was no quantum mechanics in the textbook. You look up on Google at the time, 1850 or 1900, is blank. Nothing under Q. QU, nothing. So he didn't know anything, and they tried to figure out something. He figured that if the electrons are emitting as an individual, the photons come out as individual, they could explain the black body spectrum. I won't tell you how that works. It's too complicated. But that is a time when people began to realize the photon was both a wave and a particle. For example, if I shine a light, oh, you know what? A wave and a particle. That reminds me. Yeah, I think I have it. Oh, come on. It's in here somewhere. I got one too. Okay. All right, I need a volunteer to come down here. 2 volunteers. Okay, 1. Come on down. Okay, your job is to hold this disc, all right? And not to hold it, make it, that's good, okay? A little more there, fine. Okay, your job is to shine the laser at it.
Which button?
The button is this, okay? Now, stand right where I am. Now, you see the laser beam right there bounced off, and you see one beam. What the hell happened to the other beams? Here, why don't we move the experiment? You move, both of you move. Huh? Here, move over here So move over here, both of you. So, okay. Now, look there. Shine it on the side, like this. That's good. Okay. One. Now turn that thing to 45 degrees. All right, look at that. Two spots, 3 spots. 1, 2. There you can see. Well, here you can see 2 spots at once. There's another one down there. It turns out. Why is this? Why? What happened to the beam? It's not emitting. You can't. It should be emitting. You would think if you shine a beam at this disk, it should just give you the light as it bounces off. But it's not. Anybody know? Huh? Anybody? Okay, thanks a lot. Let's give these guys a cheer. That's a Microsoft. That's, what is that? An Apple something or other. Why does it do that? Yeah.
Is it scattering the photons?
It's not really scattering, but it is diffracting. Diffraction is the technique whereby and this is something that works only if the photon has wave-like behaviors. This is something that you can understand as for the photon acting like a wave. And I don't want to just explain how diffraction works, but just trust me that it requires the photon to act like a wave to do that. Yet, on the other hand, if I shine a beam, say an ultraviolet beam, at a piece of metal, it will eject an electron. The electrons just depend on the wavelength of the light. And that means the energy of the photons. So if I shine the beam at material, it will eject electron no matter how faint the light is. The light, what's happening is the light is individual photons of the light are interacting with individual atoms and causing the material to eject the photon. To eject that electron, I'm sorry. The electron is ejected. So the electrons in a metal are typically, can be emitted or can be ejected off the surface if you shine a light that's higher than the energy holding the electron to the metal. This is a technique that's used constantly. For all light sensors, this technique is used. This photoelectric effect is important, and Einstein won a Nobel Prize for talking about this. If the frequency, nu, is sufficiently high, electrons will jump off the surface. And the minimum energy depends on the frequency of radiation. Nu is equal to C over lambda. It does not depend on its intensity. Just the frequency. And then if you tune the frequency too low, it doesn't matter how intense your beam is, none of the electrons will be ejected. All right. So Einstein proposed that light comes in discrete packets, each with an energy, h. Energy equal h nu. This is at a time when the quantum mechanics theory was unknown. There's no quantum mechanics. This is about 1905. This was his brilliant year when he produced 3 fantastic results, and I'll talk about them later. Okay. I think he won a Nobel Prize for this one. Okay. He showed also that momentum, the photon carries momentum just like mass. If I hit something, the momentum of me hitting it shows up. He showed that if an atom is hit by a photon and absorbed that photon, that gave the atom some momentum. and that is recorded. So at the time, people had no idea anything about light, but he showed it had momentum. Mathematically, he showed this. This is a simple explanation of the photo effect. All right, so how can light be both a particle and a wave? Well, that was the standard mystery. Why does the spectrum look like this? That was a standard mystery. Okay. Photons are needed, and basically you needed to have a particle and a wave nature for a photon to exist. Remember that high energy photons have a short wavelength, and low energy photons have a longer wavelength. By longer, I mean this distance is longer than this distance here. Okay, and that when you have atoms, if it makes a transition, say, from n equals 3 to n equals 2 in hydrogen, that turns out to be an emission of 656 nanometers, and that is red. So hydrogen will emit red light when this quantum transition occurs from n equals 3 to n equals 2. When the photon emits, it goes from 4 to 2. Here it skips 3, just goes down this much. The light it gives off is 486 nanometers, which is blue. So the hydrogen atom will emit blue or red and red light at the same time. And the energy is given by, well, let's see. All right, the energy is given by the energy difference of the upper state minus the lower state. And that's what you learned in chemistry. Okay, so atoms can emit and absorb radiation. For example, here's an atom that's going around, and it jumps. Well, this is pretty crummy. Let me skip that. Okay, that's the end of today's lecture. If you have questions, why don't you come down and ask me. Next time we will talk about telescopes. And, okay, I must say, let me say that you may be getting kind of tired of my emphasis on physics. The lecture next week will be the last lecture. We're going to talk about astronomical instruments, but we have to cover enough physics to understand anything about the universe. So we're going to start the planets a week from today. Okay?